So good morning, everybody. So this is my great pleasure to share our research activity on resource recovery from seawater for a circular economy. So my name is Ho Kyung-sun, and I'm at the University of Technology, Sydney. I'd like to thank Professor Sang Hyun-jung and Professor Sang Yong-nam, was Korea Membrane Society and organizing committee of this membrane school, winter school. So this is my second time to join this lectures. So this is also same as last year. I have updated a little bit of slides. Also tried to introduce the more updated progress of the resource recovery from seawater. I'm sure that a lot of people already learned a lot for membrane for last couple of days. So I look at the program and it looks like very much wide range of the membrane principle and fundamental as well as application. So this is the time for integrate your membrane knowledge and skill. So this lecture is more about the membrane application. So how we can integrate the best energy efficient desalination plant. Also how we can resource recovery from the brine as well as the AI. So this is the good opportunity to have a good future progress of the resource recovery from seawater. So these are contents. A lot of people have no idea about desalination, so just want to give a fundamental seawater constituents and seawater desalination and desalination processes. So what kind of membrane technology can be adopted using this seawater desalination and desalination water chemistry. So there are many salt and many ion can be connected with different chemistry, so that very brief water chemistry in seawater, also brine impact and brine mining. Also, my lecture is more about a little bit of fun. So I don't want to go for too much detail because a lot of people, they have a different background from industry and students and professors as well as some of the research institute. So their demand is very much diversified, so that I cannot satisfy all of them. So just to try to make sure that the basic fundamental of the desalination process, especially integration. So how we can integrate based on your learning for last couple of days, and then how we can effectively combine together. So also I just want to share a little bit of history, how this desalination is happening, and then how we can make a little bit of fun these lectures. So there is not too much modeling or equation, formula, also not much chemistry in depth, so that you can have a relax and then get the basic concept of the desalination. And if you are working on this one, so please let me know. Also, you can send the email. So I can have a more in-depth discussion together after this lecture. So let's look at the seawater. So I'm sure that a lot of people already enjoy a lot of seawater at the beach. You know, also Jinju is very close from the seawater. So seawater is everywhere. A lot of portions consist of seawater in the world. So how we can utilize this seawater. Seawater is reliable water sources and food, mineral, and energy. So we can produce the salt gradient power using the pressure retarded osmosis and RED. Also, we have a lot of minerals. Table salt. Every day you enjoy a lot of salt concentration because salt is good taster. So without salt, you cannot really enjoy your food. Also, we have a food like fishes. So a lot of sashimi and sushis can be made from the seawater fishes. So we already have a lot of food from seawater. Also, seawater desalination water. So what's the inside the seawater? So you can see 96.5% of water, and chloride is around 50% among 3.5% of salt. So which means the 35 gram per liter of the sea salt contained, and chloride is 55%, and sodium, and we have magnesium and calcium, potassium, sulfate, also a lot of minor constituents such as lithium, rubidium, strontium, any mineral, especially monovalent ion, can be dissolved in this seawater. So, how long it has been? The seawater concentration is 3.5%. So when the Earth started, at the time, nothing was there and a lot of heat. And then we got a lot of water source from the outside come back, and they brought a lot of water, and we had so many water sources and evaporate because Earth was very hot, and finally we create a lot of water sources in seawater. So at the time, raining happened a lot, so that a lot of iron like the sodium chloride, the calcium, potassium, magnesium, so all the dissolved iron washed out to the seawater. So the seawater age is around 4.6 billion years. So when the Earth started, almost at the same time, so we had this kind of seawater concentration, 3.5%, and still this is very much similar. So salt has also very strong history, 4.6 billion years history they have, and then how we can utilize this salt is one of the main target nowadays. So let's look at the seawater reverse osmosis. So you can see the United States and the Middle East country and Australia, also Asian country. So there are many seawater reverse osmosis are developing. So you can see the Saudi Arabia is the largest market of the seawater desalination. Also you can see BWRO, which is very much utilized wastewater reuse and seawater reverse osmosis. Also seawater RO can be also utilized as a second pass for the BW RO. So you can see the last 10 years what happened. So summer desalination has been very consistent, and SWRO increased significantly. Also BWRO is increasing a lot. So if you see the SWRO, so you can see the $6,000 million market. Also it's keep increasing, and BWRO also continuously increasing. So in the future, also we need more desalinated water due to climate change, growing population, and industry. So how we can manage the enough and sustainable water sources, the seawater is one of the best solutions to secure our drinking water sources. So this will increase a lot. That's the reason why a lot of people they invest in seawater desalination research as application and then commercialization opportunity. So already Professor Chung mentioned about Korea, KT. They have announced some of the desalination project which can make more energy efficient as prime resource recovery targets. So this is the global contracted installed capacity 2003 to 2023. So desalination and water reuse. Water reuse is much bigger capacity growing because you can produce the wastewater everywhere and then recycle also can be utilized on the decentralized application sources. So you don't have to send it to the centralized municipal wastewater treatment plant. So there are many decentralized wastewater uses keep increasing, which is the basically same reverse osmosis technology can be utilized. So the desalination and this is the wastewater reuse. So basically membrane technology is dominant to remove the most of contaminant as well as the salt. So we can also think about water reuse and desalinations. They keep growing the market of membrane technology application. So let's look at the reverse osmosis. So it was first seawater desalination 1956. At the time, the cellulose acetate membrane was used for reverse osmosis, and 1970 the polyamide reverse osmosis membrane using the interfacial polymerization method, and Sidney Love developed CTA membrane, and Dow Chemical developed polyamide IP method. Since then, at the time, the initial energy consumption was very much similar to distillation, summer distillation, because the oil and gas price was very low. So energy cost of seawater desalination was very similar, 10 kilowatt hour per cubic meter. And the first reverse osmosis membrane was established at this time. And then we had a second energy reduction innovation, which is the pressure exchanger. So pressure exchanger decreased almost 50% of energy cost from 10 to 4 kilowatt hour per cubic meter, so that a lot of SWRO has been applied since 2010. So that's how the reverse osmosis has been evolved for seawater desalination. If you look at the energy consumption intake, which is around 1 kilometer of intake pipeline, 5%, 0.2 kilowatt hour pretreatment, dual media filtration, or some of the multimedia filtration, 10% of the energy consumption. Reverse osmosis is dominant, like 2.8 kilowatt hour per cubic meter, 72%. Was 8% of the production, water delivery, and then total 3.9 kilowatt hour per cubic meter when you have a TDS 35 gram per liter. So how we can reduce further this energy consumption? So that's one of the major challenge of the seawater desalination. So look at the energy distribution. So when you think about the energy in terms of kilowatt hour, So in Australia, 1 kilowatt hour is $0.29. And then the Sydney desalination plant, every day we produce 250,000 cubic meter per day, which cover around 15% of our drinking water sources. So Sydney, when you come to Sydney, so if you just open the tap, so 15% of the desalinated with water combined with dam water from the Blue Mountain, and then it costs the Sydney desalination plant 15% of the drinking water, $290,000 per day, so which is very high cost. So that we have to decrease this energy cost. So this is the example of what's the 100 kilowatt light bulb. 10 hours, we just say 1 kilowatt hours. So you think about how many light bulbs can be operatable when you produce the 1 cubic meter of desalinated water, which means the desalinated water is still very expensive because the electricity is a huge amount of request. So, what's the next challenge we can think about for the innovation? First was the polyamide reverse osmosis membrane. Second generation was pressure exchanger. So now a lot of people try to tackle to reduce the overall cost of this seawater desalinated water, and this is the dry mining or AI. AI can control chemical dose, maybe pressure exchanger balance or fouling production. There are many things that AI can have to optimize the overall process of the seawater reverse osmosis. Also, others can be utilized to create the overall efficiency of seawater reverse osmosis. Others could be high pressure reverse osmosis. At this moment, only 50% of recovery is produced. So if we increase the recovery, we don't have to pay for another treatment plant, chemical cost, waste cost, so that we also consider high pressure membrane to improve the overall recovery of the seawater reverse osmosis. So that's we are now trying to make a better desalination plant. So in Australia, we have 6 desalination plants. Also, we have another 7 at this moment in the operation. And then we have a lot of medium cities. Like Sydney, we have Newcastle and Wollongong. So medium city to secure the drinking water sources. So we are also planning to have a seawater desalination plant. So many major cities in Australia, Adelaide, Melbourne, Brisbane, and Perth, they have a lot of desalination plants under operation. And look at the process. So this is the Sydney desalination plant near the airport, and this is the intake. So they first chlorinate to make sure that all the biofouling which can damage the pump or pipeline using the biofilm, and also ferric chloride. This is very much depending on your turbidity. So sometimes after severe raining or flash flooding, you have increasing turbidity of the seawater, so that you can remove the overall turbidity using iron chloride. And pH adjustment. So pH, initially seawater is pH 8, and then pH 8 is high concentration of hydroxide, which can easily combined with calcium, magnesium, or multivalent iron, which ultimately, when you have 50% of recovery, so you have a lot of inorganic fouling occurred in this reverse osmosis membrane. So pH adjustment is necessary to avoid the inorganic fouling to achieve the overall 50% of the water recovery. And dual media filtration, which is similar to center filtration, and utilize the anthracite, and you can have just a natural filtration system. The anti-scalant can be dosed with some of the fatty acid or EDTA, and some special commercial anti-scalant to avoid the inorganic scaling. Also dechlorination, so chlorinated and dechlorinate. So polyamide membrane is not tolerate with chlorine. So chlorine will attack the polyamide membrane surface, which can make a bigger pore size. So that we need to have a dechlorination, and you will have a reverse osmosis and permeate post-treatment with lime, and to add some of the calcium, and then buffer solution and fluoride chlorination, and you produce the drinking water. So that's the general process of the seawater desalination. So what we can learn here, also you have a lot of membrane pretreatment, ultrafiltration can be utilized, reverse osmosis membrane also can be utilized for the seawater reverse osmosis. So once you produce drinking water, so what's the leftover? Leftover is mostly you have a brine. So double concentration of your seawater salt ion, and this can be also recovered. So there are many people try to extract your salt ion. So C4 value from European project. Also, there is several more projects from the Saudi Arabia, like SWA, Saudi Water Authority, also Neom City, NOAA, and then there are several places that they try to extract the sea salt together with the seawater desalination plant. So if you look at the C4 value project in Europe, so they try to recover uh, magnesium and scandium and vanadium, caladium, and boron, indium, and lithium, molybdenum, rubidium, and calcium. So they have also critical material like calcium as well as sodium chloride, uh, try to extract in the brine, and then how we can utilize this seawater brine valorization. So that's the how they target to create the value of the material from the super value, and this is their general concept. So you can see the 11 material can be extract sodium chloride and then some of the monovalent ion. So they like to have some of the pretreatment process to separate multivalent ion, monovalent ion. So you can see that they have a selective calcium precipitation. This is the sodium carbonate. So chemical can be included in this brine, and you can precipitate calcium carbonate. And you have also nanofiltration can separate your monovalent ion, also some of the divalent ion. So this divalent ion, magnesium hydroxide, water can be separated from the advanced membrane crystallization. So that's the how you can precipitate more magnesium hydroxide. Also, some of the distillation process can be utilized to produce the more water. And this leftover, so you can have a more mm, this divalent ion can be extracted. Also monovalent ion, lithium, rubidium, boron can be also extracted. So there are many technology can be utilized. Polymer ion exchange membrane, selective membrane, also 3D absorbent, absorption, iron liquid or organic solvent can be utilized to extract this kind of multivalent ions. And then you have a monovalent ion, which is the more challenging to recover. So you can use binary extraction, solvent extraction, synergistic solvent extraction, also polymer ion exchange membrane, also 3D absorption, also ED bipolar membrane can be utilized to extract the monovalent ion. So that's the how they like to implement as a cipher value project to recover different source. So you can see what's the dry mining in terms of this concentration and versus price 1 kilogram per US dollars. So you can see this is a high concentration, this area. Also, this area is high value. So 1 kilogram is around $10. 1 kilogram is $10,000, which is the rubidium chloride. And $10 is also good enough for kilogram. And lithium carbonate, bromine, and magnesium. Also, even though it's low concentration, low price, but the concentration is relatively high, such as sodium chloride, because high concentration of seawater, and calcium carbonate, calcium sulfate, potassium chloride. So a lot of calcium, sodium chloride, magnesium related compounds can be generated with the high concentration, even though the value is low. So for example, like Neom City or Saudi Water Authority, they based on their cost benefit. So when you have 1 cubic meter water, desalinated water, it's around you need the energy cost or chemical cost. So it require almost $1 for the cubic meter production. However, so what's the price of your drinking water? 1,000 liter. So you pay around $1, which means the water cost is still very cheap. Also, if you look at Saudi Arabia, in fact, they don't really charge your water cost because this is almost free. And they cannot get a lot of cost benefit. However, when you recover most of sodium chloride, then you can say that your recovery is almost 98% or 99% of water, and then double production, as well as you produce a huge amount of sodium chloride. Sodium chloride is around $0.2, 1 kilogram. So you will also get a lot of cost benefit if you sell this sodium chloride, which means the sodium chloride itself. So if you sell all of them, which recover from desalinated water, so even you don't have to pay for your water cost, which is relatively low. So that a lot of people try to recover this kind of different salt. Also, this is the Neom City diagram of the resource recovery. Also, this one was initially proposed by the Saudi Water Authority. So let's say they tried to develop the world's largest desalination plant, 1 million cubic meter per day, and go through the dual media filtration, cartridge filter, and nanofiltration, monovalent ion goes through the SWRO, and then divalent ion, multivalent ion goes to the brine uh, harvesting plant. Also, you have a increased number of uh, water recovery because the overall salt concentration is low, and then you can use BWR produce the drinking water. Also, we have a leftover of monovalent ion. So it comes to this brine mining plant, and first utilize the membrane brine concentrator. So several people have developed the membrane brine concentrator. So in general, seawater reverse osmosis and is under operation at the 70 bar, which means around 40% or 50% recovery of the reverse osmosis. And people try to increase the overall the brine concentration membrane technology. So they increased around 120 bar, 150 bar, so that you can increase your overall concentration of this brine, let's say 2 times higher than seawater, 70 gram per liter, can be increased up to 150 gram per liter. Or nowadays, the maximum is 200 gram per liter. It's also possible using membrane brine concentrator, using the circular closed circulate uh, reverse osmosis technology, or high pressure, ultra high pressure reverse osmosis membrane. It utilize the multi-stage, first stage, second stage, third stage, increase the overall high concentration to reduce the also constant polarization, and then you can have a maximum around 150 gram per liter to 200 gram per liter, and you can go to the next crystallizer, basically thermal crystallization, and you evaporate your water and keep creating your salt, and then you can have a sodium chloride 25% brine, and then crystal sodium chloride salt. Also, you can produce the bromine, which is around 3,600 tons. So if you go back to the slide, price versus your concentration. So 1 ton of the bromine was almost $10. So every day you produce the $36,000 for bromine value of 1 million cubic meter per day of the seawater desalination. So bromine produced around $36,000. Also, you have a sodium chloride. Here is a 25%, and then crystal. They could separate because of the sodium chloride can be utilized many different applications. Not only table salt. So a lot of people use table salt to increase the good taste of the food. At the same time, sodium chloride can be used as a chloroalkali method, which means this sodium can produce the sodium hydroxide, and chloride can produce the chlorine using this alkali method, and then using this electrolysis processes, so that it can be used as a chemical, pharmaceutical industry. Also, you need a lot of salt. The electrolysis can produce the hypochlorite and sodium hydroxide, alkali, and then low pH, and then you need a lot of chemical to reduce the overall pH adjustment at the desalination. Also, you need to precipitate your calcium hydroxide, magnesium hydroxide, so sodium hydroxide, and hydrogen chloride can be produced from this 25% of pure uh, sodium chloride brine concentration. So there are a lot of applications. The Neom City, they try to develop this technology, and then they already completed the phase one and then phase two. So try to develop the phase three. At the same time, also they like to have a more the rubidium or lithium recovery after this phase completed. So look at the see what's the best way to recover. So you can see the again the price of US dollar for 1,000 cubic meter, and this is the what could be the best value we can produce. So Saudi Water Authority already they have identified so magnesium metals, magnesium salt, also magnesium, calcium. So seawater contain a lot of sulfate, chloride, and pH can adjust, and hydroxide can be utilized. Also carbonate CO2 or CO2 can be carbonized and then combined with the magnesium. So calcium, magnesium, salt, so they have a different value. So this can be also considered what kind of the salt could be the best way to recover. So chloroalkali method is useful. Already I mentioned about 25% of sodium chloride can be utilized, recover from the desalination plant brine, and you have this method can produce the sodium hydroxide value is relatively high because also this is the very hazardous material, so delivery cost is very expensive. So if you can produce your sodium hydroxide on the spot, that will be very much cost effective. So sodium chloride, and using this method, sodium hydroxide can be produced. Also magnesium metal, also magnesium different salt can be produced. Also HCl from this method, and this can be used for the seawater desalination, pH adjustment, and you can also reduce a lot of the inorganic fouling as well as the chemical cleaning. So seawater desalination plants require a lot of the chemical cleaning processes. So HCl or sodium hydroxide can be used on the spot. Also sodium chloride, rubidium chloride, and potassium sulfate, calcium chloride, bromine. So these are the one of the uh, best potential value can be produced, and most of people they target on this material: sodium chloride, bromine, magnesium, calcium, and others. So magnesium sulfate. So when you have a brine, so this is the most um, easiest way to you produce. Also sodium chloride without any chloroalkali method. So sodium chloride itself is just good value. And then magnesium chloride, rubidium chloride, bromine, calcium sulfate, potassium, calcium carbonate, and water. So this the value. Yeah, you can just produce the water, which is the almost 100% of recovery. So if you sell this magnesium chloride, which already more than 5 times of the price you can cover, which means you don't have to uh, the consumer pay for the water cost because you can produce a lot of the value from the salt. So that's the how the Saudi Water Authority they try to develop the best technology and the cost-effective process to make this potential revenue using seawater brine. So let's see a little bit of uh, chemistry. I have 20 minutes left, so I can make a little bit more detail. So when you have this carbonate, how this can be utilized in the seawater desalination plant. So let's see the dissolved organic carbon. So a lot of people also look at nowadays the CO2 because of climate change. So CO2 is the one of the big problem. So CO2 has been increased for last couple of decades or 100 years significantly. And then when you have this CO2, so you can see the CO2 chemistry equilibrium graph here. So when you have a pH, so seawater pH is around 8. So you have a lot of bicarbonate concentration. So now CO2 is increasing because of climate change. And what happened is the CO2 is keep increasing, and this CO2 is continuously dissolved in seawater. So which means the seawater concentration will be continuously lower and lower, so that this can have a very big problem of a lot of calcium carbonate production, which is the major source from the lobster or oyster. A lot of people try, a lot of the seawater animals produce this kind of calcium carbonate for their skin. And then this is the one of the very big problem. So this pH, when you have a CO2, CO3 minus carbonate concentration, also you increase the overall pH. So a lot of people try to utilize the CO3 carbonation, this carbonate, to increase the pH combined with the calcium and magnesium, so that you can produce the calcium carbonate and the magnesium carbonate, which can easily precipitate. So that's the how this CO2 can be applied for this seawater mining brine concentration. Also, you can see the calcium carbonate looks like this scale structure. Also, this is the calcium sulfate. So you can see the different way of their crystal. Also, magnesium carbonate. And to avoid this kind of calcium carbonate, magnesium carbonate in the reverse osmosis, so we utilize the anti-scalant for the surface active material that interfere the precipitation reaction in three primary ways. So calcium carbonate, when you have a high concentration, high recovery of your water, and then you create this kind of inorganic scalar, threshold inhibition, crystal modification, and dispersion. So people utilize a lot of different way of the commercial anti-scalant. So one of them is sodium hexaphosphate, is hexamer of the composition, so they can be easily combined with the calcium here, replaced with sodium, so that you can avoid crystal growth of this kind of the inorganic scalant. Also, chlorination, dechlorination. So what happens is you chlorinate it and then dechlorinate it. You can add SBS, sodium metabisulfite. So this can combine with the chlorine. And then you have a sodium sulfate, and then this uh, molecule can also change the sodium sulfate and then to HCl, so that you can easily remove your chlorine to ionized form, which is the normal oxidation active process. Also, you can use the granular activated carbon, so that a lot of people, they still utilize the dual media filtration or multimedia filtration as a pretreatment, because organic compounds attached with your media filter combined with the chlorine react with the carbon. So as you know that the seawater has around 1 milligram per liter of seawater organic compound, and that this can be also react with chlorine, which can be ionized your chloride form, so that you can naturally also remove the active chlorine, which is the very strong oxidant, and this oxidant can be automatically, you can dechlorinate it. But people think about the microfiltration, ultrafiltration was utilized for the pretreatment. Nowadays, because of the brine mining purpose, nanofiltration was utilized. Nanofiltration basically similar like polyamide membrane is utilized, and then this also has a very strong oxidant uh, performance. So dechlorination is necessary. But when you have microfiltration, ultrafiltration, which is basically PVDF or PP membrane, which has a very high tolerance of your chlorine. So microfiltration, ultrafiltration, even ceramic filtration, it's okay to have a chlorinated compound. But when you go through the non-porous membrane, such as nanofiltration, reverse osmosis, will have very much easy to damaged with the chlorine, so that you need to make sure that the dechlorination process. So a lot of people using still media filter because of the one of the reason of this one, and then still the microfiltration, ultrafiltration, very consistent pretreatment, overall reverse osmosis performance is better. It's true because they remove the more larger molecule which has a high potential of the organic fouling, so that ultrafiltration looks like nowadays a lot of pretreatment used, but there are always cons and pros to utilize the different way of your pretreatment method. And this is the also remineralized. So when you have this produced water, very low concentration of the TDS, so it's mostly sodium chloride. So you need to have a buffer solution. So people try to incorporate the magnesium and calcium, which is the good quality of drinking water. So magnesium has very good performance of the heart disease. Also, this is the good for some of your diabetes, so that magnesium is our body important material. So magnesium is incorporated, and the calcium was a good buffer solution, which can reduce your pipeline or pumping corrosion impact. So there are a lot of adverse impact you have when you have only sodium chloride in your water. So magnesium, calcium, using this calcite, limestone or sodium carbonate or CO2, calcium chloride, and this solution can be combined with the post-treatment, so that you can improve your overall quality of the drinking water. So that's the general our the desalination process. So I have a 5 minutes left. So let's go for a little bit more detail, the brine mining. So let's look at the brine mining. So where is the place? A lot of people are utilizing the brine mining. So you can see ocean provide 40% of the all magnesium, and one third of the water supply salt come from sea and oceans. So cooking salt, potassium salt, bromine, and iodine. So you can see the cooking salt. So this is number one. So there are many cooking salt from the seawater, even in Australia. And some place, Korea, Japan, China, and if you see this uh, place number one, cooking salt, so there are many production line. Mostly they utilize the evaporation pond, which is not connected with the desalination or brine. So they just utilize seawater as it is and the evaporation pond and produce the cooking salt. So if you see this area, Indonesia, so there is no cooking salt because this area has a lot of raining. So tropical area, so that a lot of raining for whole year, so that they cannot sustain their evaporation pond, so that they have no the cooking salt factory. So they have a RO brine combined with the crystallizer, and they have produced cooking salt using the brine with the seawater desalination. Indonesia is one of the very represented brine mining. They produce mainly cooking salt, and then this Middle East area, they produced a lot of uh, the project like Saudi Water Authority. They have a pilot, and then they want to target bromine, potassium, magnesium, and then now it's still on the pilot scale. The end user is very important to uh, purchase this potassium, magnesium, bromine to replace our brine mining market. And then this is the concentration in precipitate and calcium carbonate. So when you have around 50 gram per liter, even calcium carbonate is not that much simple. So there are three different precipitant can be produced. So butterite, aragonite, or calcite. So butterite is the initial, the least thermodynamically produced crystal form. And if you have a little bit higher temperature or dry condition, also they produce the aragonite and calcite. So it depending on your crystal structure and size, also your bonding strength of your material, you can produce from the seawater brine. So calcium carbonate, calcium sulfate, and sodium chloride 100 gram per liter, magnesium sulfate, calcium chloride, magnesium chloride. So in terms of your salinity concentration, so you can produce automatically. So easily you can have a precipitate with the different concentration of calcium carbonate, calcium sulfate. So this is the sequence of the precipitation of the mineral from seawater. Crystallization initially easily produced, then you have calcium sulfate and sodium chloride, magnesium sulfate, magnesium potassium chloride, magnesium chloride, and you can finally try to make a sequence of this precipitation. Also energy consumption, BWRO, SWRO, and ultra pressure retarded osmosis, ultra pressure rise reverse osmosis. So you can see around 5 to 10 kilowatt hour per cubic meter. And then mechanical vapor repression and then multi-effect evaporator. Also, you have a summer process, so you can have a very high energy consumption, 30, and crystallizer is around 60 kilowatt hour per cubic meter. So a lot of people try to target. You have reverse osmosis, so like automatically assisted reverse osmosis or ultra high pressure reverse osmosis can be saved a lot of your energy cost. So how we can have a further development of this high pressure RO or osmotically assist the reverse osmosis would be the future research area you can consider. But no matter what you do, and then when you have complete the crystallization, so you need to have a summer crystallizer, but you can reduce a lot of volume from the low energy, high pressure reverse osmosis. So this is the good technology you can utilize. And this is the generic heat charge already mentioned about thermal membrane, others. And this is the Neom City. They want to produce this kind of program to make all the resource recovery from the calcium carbonate, magnesium hydroxide, magnesium potassium chloride, lithium chloride, rubidium chloride. So that's on the phase 2 stage of their pilot scale. Also magnesium relatively easy to you can recover. Also bromide can be converted to bromine. So bromide concentration is 100 milligram per liter of seawater. So you can combine with the chlorine, and then you can easily produce the bromine. So you can have a liquid-liquid separation to have a very high purity of the bromine. Bromine is around $10 per 1 kilogram, which is the very high value of the year. Also, rubidium is $10,000 for 1 kilogram. It can be used for the different GPS and medical application, so that a lot of people are utilizing this rubidium recovery. So Prussian method replaced with potassium rubidium is currently utilized, and then we are also developing this technology to make more commercial opportunities. Also lithium is even though still low concentration in the seawater, 0.2 milligram per liter. So most of commercial application you need around 50 milligram per liter, 100 milligram per liter, which is the salt lake. So still seawater is low concentration, but when you have almost crystallized stage, dry mining, so you have around 5 milligram per liter, still very low. So it's a little bit long way to go commercial opportunity of the lithium in the seawater. So that's I want to skip most of micro concentration of our resource recovery. Also, this is the QR code. Yeah, you can also look at some of the video, which I didn't explain detail of the lithium, rubidium, bromine concentration due to time limitation. So you can go there and you can also see the more detailed low concentration resource recovery method. So thank you for your attention, and I wish you all the best and a happy new year for the 2 weeks later. Thank you very much. Thank you, Professor Zhang. Bye.